Hello and welcome back. In this video, I'm going to show you how can we use an unscented Kalman filter to estimate the states and identify the parameters, some of the parameters of this nonlinear Bouc-Wen model. Nonlinear Bouc-Wen model is a mathematical equation that will be used to describe the nonlinear hysteresis behavior of any system that has this kind of the physics. In this equation, for this Bouc-Wen model, the restoring force, which is described with RT here, it does not only depend on the linear relationship between the displacement and the force. The Hooke relationship. It says that the force also depends to the history of motion, and that's the reason you see the loop, and it's not just linear, it's not a straight line. The relationship between restoring force and the RT and the displacement, for example, here, if I want to write it, this is XT, and this is RT. I don't want to go into the detail of this Bouc-Wen model. This is out of the scope. I just chose this system because it's highly nonlinear and it's not easy to calculate the derivative and write it in a matrix form. And I want to see how can we use Kalman filter, unscented Kalman filter, to estimate the states and the parameter of these system. Then I showed the schematic of the system here, and I assume that we have an accelerometer here. And we measure the acceleration of the vibration. Also, we know the FT here. Then we know the X double dot. We know the mass, okay? But we don't know Cx dot or we don't know Ke. Then if I write my X state vector, it will be my displacement, my velocity, as K. Here we defined it with Ke, C. Also, let's assume we don't know the gamma and beta. Okay, these are the states and parameters we are looking for to see. Let's take into account something else. For example, I take into account the Z, BW, Ke, C, gamma, and beta. Okay, these are the parameters and states. These are the parameters. And these two are the states we are looking for to estimate and identify, and we call it a joint state parameter identification problem. Then we have the measurement, which is coming from the sensor. We know the excitation. Then we have the equation of the motion. Then what we need to write this equation in the stated phase form. Then, as I said, in the unscented Kalman filter, we do not focus on linearizing this nonlinear function. Instead of that, we assume we have a prior information, use this prior information, generate the sigma points, and propagate these points in the stated space in the transition function, which is in the stated space form, to predict the mean and variance of the states, and to calculate the mean and variance of the predicted state and the mean and variance of the predicted output. Then first of all, I need to write my transition function. Okay, what I do here, I define these states and parameters as x1, x3, x4, x5, x6, and x7. Okay, I write the equations in the continuous domain and be converted to discrete domain later. Then x dot, which is my state vector here, I write it in a capital form. X dot will be equal to x dot, x double dot, z dot, Ke dot, C dot, gamma dot, and beta dot. Okay, x dot here is equal to x2. Yes, x double dot, we need to write we need to convert this equation. Then it will be ft divided by m, which we know it, minus RT is alpha. KE here is the X4, I think, and XT, which is the X1, to the minus 1 minus alpha, KE, which is again X4, XY, which is constant, and we know it, and ZBW, here ZBW is X3. Yes? Then minus X5, X2, all of these divided by M. Yes? Then what I did, I separated the X double dot and wrote it based on the state vector we have. And we write the same thing for ZBW. Then Z dot BW, we have the expression here. I don't want to write it here, but I just, you can do it, but I write it as Z dot BW, which we have the expression as you see here at the top. You have what you have to do is just replace the parameters you are interested. You are looking for with the state vector, and k dot will be 0, c dot is 0, gamma dot is 0, and beta dot is 0. Right? This is our transition function. You see, I didn't try to write the equation in the matrix form. I just wrote the function corresponding to each parameter and state I'm looking for to estimate or identify. Then this is the x dot. Then we need to discretize this nonlinear function. And and as I said in the previous video, x n plus 1 will be state vector xn plus f dt or delta t. This f is this function for x dot. Okay. Then after writing the equation in the continuous domain, the arbitrary transition function, if you want to use Euler scheme, you use just simple expression to write your transition function in a discrete format. Then after that, we need our measurement function. And the measurement function here, if you assume we measure the acceleration, then we have to write down this equation in another format to predict the measurement. Then the y, which is the x double dot, is equal to, as I said, I will write this one, 1 over m ft minus rt, which we write it is alpha x4 x1 minus 1 minus alpha x4 xy, which is a constant, x3 minus x5 x2. You see, this is my measurement function. Again, I just wrote it as a function. It's not a matrix or anything. Then what we have to do is, okay, let's say it's for x, start ZB, W, K, C, gamma, and beta. Yes, these are the states we had. The length of the state vector is 7. Then the sigma points will be 2 times 7 plus 1, which is equal to 15. We make initial guess, x0 and p0, and implement the unscented Kalman filter. And I'm going to show you. Wow. First, these are the states: displacement, velocity, and hysteresis displacement. Then which are the x? Then this is the I write it here. This is x. This is x dot, and this is I'm gonna write it here for you. ZBW. Yes. These are the states, and these 4 are the parameters. Which the first one is k, gamma, c, and beta. And you see at the beginning, for example, for k, the initial k value we assumed was something around close to 25, while the ground truth is something between 40. And the unscented Kalman filter was able to catch the ground truth. And you see for all the cases, the initial value is a bit far from the ground truth, but the Unscented Kalman filter was able to catch. And here is the displacement geostoring force curve. And you see that the Unscented Kalman filter was able to reconstruct the curve, and which we compared with the ground truth. As you see here, we were able to use Unscented Kalman filter here to estimate the states and the parameters of a highly nonlinear system. This is not the things that you can do using linear Kalman filter and Unscented Kalman filter. Maybe you can try an extended Kalman filter here, but as a challenge, but I don't think it's gonna work here for you. As you see here, we have a shadow around around the line for the parameter. Actually, the lines you see is the corrected mean for each parameter, and the shadow we have is the uncertainty of the estimation. Then this is the things that I was not showing or talking about so far. But conceptually, what it means, you are correcting your prediction, you are showing the mean of the prediction. Once we do you remember I said x is x hat plus Kalman gain y minus y hat. Yes, this was the magic equation in the Kalman filter. This x, which is shown here by this line, is the mean. Technically, the line is the values corresponding to this, whatever is inside this x vector. And at the same time, we had a p, which was the uncertainty of the correction or uncertainty of the true state. And here, what you see as a shadow is the estimation uncertainty. Then Kalman filter, as I said at the first video, in addition to predicting the mean, it gives you the level of the uncertainty of the estimation, which you can use it for risk-informed decision making. For example, if you have a system and you are quantifying the level of the specific parameter, and you want to quantify the level of the change of that specific parameter, and you want to make sure that your estimation of the change is accurate, then in that case, having a sense of the uncertainty of the estimation helps you to make a risk-informed decision. For example, for this algorithm, as you see at the beginning, the shadow is white. It means your estimation is not accurate. But once you are at the tail or at the end of the iterations, you see that the shadow is getting narrower. It means that the Kalman filter is getting confident about its estimation. And that's another advantage of any type of Kalman filter technique that helps you to quantify the uncertainty and to make a risk-informed decision. Now I'm gonna stop here, and in the next video I try to use Unscented Kalman filter to estimate the states and parameters of a damped linear mass spring system, which is excited with earthquake data. And after that, I try to see if are we able to still use Unscented Kalman filter to quantify if, for example, assume during the earthquake, the building is the three-story building, one of the floors is damaged, the concrete is cracked, and the stiffness value decreased. Are we able to use Unscented Kalman filter to quantify the level of the damage in that specific floor or not? These are the things that I'm going to talk about in the coming videos. Thank you very much.